For the dot product implementation, we need to understand the piece of calculus behind the backward pass. Because for the forward, things go very easy. We utilize the dot product from the NumPy. But for the backward pass, we need to understand the calculus behind. And we know that dot product is just two matrix multiplication. We have matrix A and matrix B. It means that we need to apply the derivative or the gradient, whatever, for both of these variables. And in first case, when we compute the loss with respect to A, we just have the result our loss times the B transpose. But the implementation of this B transpose little bit different from the usual transpose. Because for the 1D case, we can face with the scenario when two vectors produce the matrix. It calls the outer product based on the NumPy definitions. If you wanted to know more details about the dot product of two matrices, I have a video about this, because it's a little bit different topic. But basically, this outer just compensate case when we produce the matrix based on two vectors. In case if we have the vector vertical vector times the horizontal vector, we basically produces the matrix with the corresponding dimensionality of the vectors. But for the case when the dimensionality more than one, we can't just utilize the transpose. Because for the case more than two dimensions, we need to just swap the last two axes. That's very important, because if we utilize the transpose for the 2D, things goes well. We just swap the dimensions and it works fine, no problem at all. But for the 3D or 4 even in more dimensions, we have big troubles, because we need to swap only two last pieces. We don't need to transpose the whole bunch of dimensions. It's incorrect behavior for this calculus pieces. We can implement this matrix multiplication function, and then we move this piece of code to the tensor class. Okay, first let's create a variable output, and we need to call the a.data.product with b.data, because we can utilize this add symbol as the dot product between two matrices, between two NumPy arrays. Let's create the variable requires gradient, and if one of the tensor, let's say that A requires gradient or B requires gradient, we just activate the gradient, computational graph for the final result. Okay, and dependencies as the list of dependencies. Okay, and we check that if A requires gradient, we build the gradient operation for this node, for node A, for matrix A. For the backward pass, we need to define the backward A. We have the gradient parameter as the NumPy and the array, and we will return NumPy and the array. Okay, and for the implementation, we need to check if B number of dimensions more than 1, because we need to keep in mind that for the node A we compute the derivative with respect to A, and it means that we have only one, yeah, it's just like an x times b, yeah, function with respect to the derivative of the variable x, and we have only b, yeah, in this case we just compute the derivative accordingly with the calculus rule. So, and for the if dimensions of the matrix B is more than 1, we return the gradient times gradient dot product with the B data dot swap axis, and we swap the axis -1 and the -2. And for the dimensions that equals 1, we need to return numpy outer product of the gradient and b dot data dot transpose. Oh, and we can utilize the squeeze, just not to add more dimension than we need. And last step, we need to append to the dependencies leaf, and we know that value for this leaf is the matrix A, and the gradient function is the backward step for the matrix A. Okay, now I think that everything looks nice. And now we need to do something similar, but for the matrix B. If matrix B requires the gradient, we need to create the function backward B. Okay, we have the same gradient parameter, but right over here we need to check the variable A, yeah, because for the B we have quite similar, yeah, but little bit different action, yeah. We need to multiply A transpose times the gradient, the derivative of the loss, yeah. And derivative of the loss is the gradient, and we need to multiply the dot product of the A data swap axis -1, -2 dot product with the gradient. It's exactly what we need to utilize, yeah. It's right over here, yeah, the dot product between the A transpose times the derivative of the loss, yeah, or in the code we implemented it like this. Okay, great. And for the outer product we need to utilize the A data transpose, yeah, with the gradient. It's for the dimensionality that equals 1. We just compute the outer product of the matrix data transpose with the derivative of the loss, or our gradient. So, and for the value we add to the dependencies value B and the backward B as the gradient function. And finally we need to return the tensor with the output that requires gradient and the dependencies list that we fill with our dependencies A or B based on the requires gradient flag. Okay, now we can copy and paste it to, let's say, right over here. Like a static method, we paste this matrix multiplication method. But I want to make a convenient way inside our tensor to make a dot product, yeah? And let's define a dot method. As the first argument we have the self, and as the second we have the other as the data type, and we return the tensor data type back. Okay, and we need to return the tensor dot matrix multiplication between the self, and we need to be sure that this other is the tensor, yeah, and we can run this matrix multiplication operation without any potential problems, yeah. And we need to have some mechanism to prevent, yeah, to convert this data to the tensor, just to keep the consistency between the running operations. Yeah, we can't run the matrix multiplication between the tensor and, let's say, integer. Yeah, it won't look, it doesn't look good. Yeah, so let's create one more static method, probably somewhere here. Let's define the static method. Let's call it, let's say, data gate, and we have the data, and we mark it as the data type, and we return back the tensor. Yeah, what do we need to do? We need to check that if the data instance is tensor, if we already have a tensor, we need to return the data. But if we have something different, we need to return the tensor, and we just put this data to the tensor. Because as far as I remember, inside the tensor we can provide the data, and we run this build and the array, and it's totally legit operation. It converts the data to the correct data type, preprocesses everything that we need, and return back the legit tensor object. Okay, everything should work fine. So in our case, right over here, we need to call the tensor dot data gate and wrap this other by the data gate. And right now it's totally legit operation matrix multiplication, because we can be absolutely sure that this other gonna to convert to the legit tensor, and this operation will work fine all the time. And the last piece of implementation, we can overload the add operator for matrix multiplication. We have this mul magic method. We have self as the first argument, and let's say that we just keep the same data types, yeah, and arguments as for the dot operation. And we need to return just self dot other. And I hope that this just totally legit operation, yeah. When we run the add operation between the tensor and the tensor, we will call this dot, and everything looks nice. Yeah, we just return the static matrix multiplication, and this matrix multiplication totally legit. Yeah, it produces the right output for the matrix multiplication. Okay, I think that this chain looks nice, yeah, and we are ready to test our linear layer, because we have this dot product, and we are ready to finish this matrix multiplication. Because right now, probably when I click, yeah, with the control button pressed, I just move the cursor to this matrix multiplication overloaded operation. Yeah, it's just implemented, and we can see how it works now. Yeah, it's just right over here. Yeah, we have this operation, yeah, and it returns back the tensor, and we have the type inference based on the result that this matrix multiplication produces. Yeah, we have this tensor as the result of the dot product computations. Okay, so everything looks nice, and we have this output, but we need to add one more step, because we need to add this bias term for the output, and we need to check that if self.bias is not none, we are ready to add this bias to the output. Yeah, let's just add to the output our self.bias term. And I hope that this plus sign works fine, even if the dimensionality of the output is not the same as the dimensionality of the bias term, because we have the broadcasting, yeah, and broadcasting will handle it, and I hope that it works fine, yeah. And you can check my video about the matrix multiplication, about the broadcasting, yeah, because it's the whole bunch of information behind these operations. Okay, and for the last step, we need to return the output. And I think that right now we have just linear linear layer that looks totally legit. Yeah, it handle the matrix multiplication right over here to produce an output, and also we have this bias term that we add to the output. But this is not everything that we need to have to implement the neural network, yeah, and I think that we need to do a little bit more work.